All right, the second section we're going to take a look at today is section 3.2. This is a gentleman, his name is Rolle. All right, this is Rolle's theorem. It's not Rolle's, by the way. And we're also going to take a look at another theorem called the Mean Value Theorem. These two theorems are very related. They're actually just a special case of one of them. Rolle's theorem is a special case of the Mean Value Theorem. But we're going to start with Rolle's theorem because it's a little bit more easy to work with as it starts. So Rolle's theorem says the following. Suppose that f is continuous on the interval from a to b, and it's differentiable on the open interval a to b, and f of a is equal to f of b. So it starts and it ends at the same location, much like my last example with cosine, right? Started and ended at the exact same y value. That's the image you have in mind. Then if there is a number between a and then, I'm sorry, not if, then there is a number between a and b where the derivative will be 0. And let me draw the same picture that I just drew on the last slide from our previous lesson. It was something like that. They're saying here a and here is b, right? The end points. They're the same y value. That there will be some location, and we already saw it last time, where the derivative is 0. Has to happen. Okay. So of course that's not specific to trig functions. It's only specific to the fact that the functions are continuous. Okay, no picking up my pencil in between, no jumps, and they're differentiable. So no asymptotes, no sharp turns, that kind of stuff, no holes in graphs. All right, cool. So we're going to decide on the following, whether Rolle's theorem can be applied to the closed interval. So in order to be applied for Rolle's theorem, there have to be some conditions met. It has to be continuous, and it has to be differentiable. And do you remember when we had to deal with some conditions like this on the first test, and you had to test for them? It's very similar. You had to test and make sure on that one, I think, that it was continuous, and something of the endpoints, that the endpoints were surrounding the point you were looking at or something like that. It had two pieces that you had to test for. So we're looking at the same kind of thing here. We have to test for being continuous and being differentiable. And then if it has those two conditions, we're actually going to find where's the derivative equal to 0. Okay? So is this continuous? Yes. Is it differentiable? Yes. Now the question is why? The answer is the same for both y's. Why is it continuous and differentiable for this function? Because it's a polynomial. And we already discussed back in chapter 2, I think, somewhere, maybe chapter 1, that continuous and differentiable, continuous anyway, automatically for all polynomial functions, and then in chapter 2 that polynomial functions are always differentiable. Okay, so we get those kind of for free. The third condition, I didn't highlight this one, but the third condition is that f of a is, that f of a is equal to f of b. That the endpoints that I'm given actually have the same y value. So I actually have to test f of 0, and I have to test f of 3 and make sure I get the same y value when I do them. So if I plug in 0 into this function, what do I get? I get 0. That one's pretty easy. How about when you plug in 3? You do get 0. And so in fact, these two, they don't have to be equal 0, but they do have to be equal, and that's the important thing that we see here, is that they're equal. So I've got all my conditions met. Condition number 1, continuous. Condition number 2, differentiable. And condition number 3, endpoint values match. So Rolle's theorem applies. Okay, so what do we do? Well, then according to Rolle's theorem, I should be able to take the derivative, set it equal to 0, and there will be some x value that shows up from this derivative equal to 0 that's going to be between 0 and 3. So we're going to find it. So what is the derivative of negative x squared plus 3x? Negative 2x plus 3. I feel like we saw this one a little bit ago, didn't we? And where does this equal 0? Three over 2. And what do you notice about 3 over 2? It is between the 0 and the 3 that we started with, right? 0 is less than my 3/2 is less than my 3. Rolle's theorem said there would be one, and we found it. Okay, let's check the next one. Different function. Do you know what kind of function this one is? We've been asking you guys that question a lot today. We've seen polynomials. We've seen rationals. This is neither one of those. It's what? It looks like it's exponential. It's not usually how we think about it. We usually think about it rewritten in a different way. Yeah, it's a radical function is what it is. Yeah, it's got a radical in it. So some parts of radical functions are okay. They're nice and smooth, and some parts aren't. It depends on the interval you're looking at. So that's what we have to check, as well as this continuity differentiability business. So my interval goes from negative 8 to 8. If you want to think about this, this is the cube root of x squared, if that helps you to think about it in that form instead. We need to figure out if this is continuous or if it's differentiable. So, well, not if, but both of them. So we check for continuity. I'll just abbreviate. Continuous. And we need to check for differentiable. So, is it continuous? Can I plug in numbers from negative 8 to 8, or is there any location where I cannot evaluate this function? No, there isn't. This works just fine. It's continuous. But is it differentiable? Now, being differentiable is a trickier question.
No.
It is not differentiable. Do you know why, or what error, what problem are you seeing, Emma?
Okay, so I graphed it.
Good. What did your graph look like?
Okay, so it has like the square root values, like except on both sides of the x-axis. Yeah.
Does it look like that? Okay. Yeah, exactly. And so if I sort of put in some axes here, does it look like that? Does it go below? It goes below a little bit. I think it does this. Can you tell?
Well, it's at x equals 0.
Oh,
Y
I see what you're saying. You would like for me to move this over here.
equals 2.
That work? Awesome. Okay, but it does dip below the x-axis just a little bit. Yeah. Okay, so this is roughly what the graph looks like. Don't hold me to the exactness of it, but it's pretty close. It goes from negative 8 to positive 8. And you notice that there is one place in particular where it is not differentiable. Where? At x equals 0, right? I actually have a sharp turn there, and sharp turns are not differentiable. So this one is not differentiable, and the reason is because there is a sharp turn. It's also, you could call it a cusp, and it's happening at x equals 0, and that's actually happening between negative 8 and 8. In particular, that's the problem. So if you continued, that would be okay. You can test the endpoints at negative 8 and positive 8 and see what they are. It actually works. The endpoints do match, but this already failed. It has to match all three conditions. So Rolle's theorem does not apply. And in particular, this is the one where it fails, the differentiable one. Yes, sir? No, what you could do is you could find the derivative and see what happens. So let's say, for instance, you didn't think to look at the graph, or maybe you didn't have your calculator with you and you weren't sure what to do next to make that sort of claim. And so you just went on and you said, okay, well, let's just see what happens when I find my derivative. So if you were to take this derivative, what would you get? Because to the minus what? 1/3, right? Good. And then the rest of it's 0. And if you then looked at what this actually is, this would be 2 over 3 cube root of x. So far, so I mean, we're good. The problem is that there is an x value that I can't plug into this. I can't let x equal 0. It would make the derivative undefined. And the derivative being undefined means it wasn't differentiable at that particular point. So that's a more algebraic approach, and the other one would be more graphical approach. Okay, everybody good with those possibilities there? Okay, got one more, a trig one. Same directions. Similar to the problem on the last section that we did. So again, continuous, differentiable, and then we would need to check that f of 0 and f of 2 pi in this case are the same. So these are the 3 checking points. Is it continuous? Yes. Is it differentiable? Yes. And what is the reason why? Yeah, because it's a sine function or because it's sinusoidal. Yeah, that's good too. Yeah, it's a sine function. Sines and cosines are continuous and differentiable. How about tangent? What if I had tangent? No, unless it happens to be between the interval where it is, right? There's lots of asymptotes for tangent, and if I narrow down my interval tight enough, I'd be okay. But if I look at too wide of an interval for tangent, I wouldn't be okay. So it would be contingent upon the interval we're looking at. All right, how about f of 0? That's 0, and f of 2 pi, also 0. So these are equal. Oops, do you have a problem? Oh, it says sinusoidal. If you don't want to write sinusoidal, you can just say it's a sine function. That's fine. Frankie said sinusoidal, so I wrote it. Sinusoidal just means it has that sine curve. So cosine curves are actually also sinusoidal. But, yeah. Okay, so Rolle's theorem applies, right? So now what? Well, now I can find a derivative and find the location between 0 and 2 pi, and there will be one where the derivative is equal to 0. So what is the derivative of sine of x? Yep, cosine of x. And where is cosine of x equal to 0 between 0 and 2 pi? Yeah, there's a couple of locations, and they both happen to be on the interval that we were looking for. So I have 2 c values on this interval. I'm guaranteed to have 1 by Rolle's theorem, but I could have 2 and or more, and I do on this one. Okay, so Rolle's theorem had this condition that said that we have to be continuous and differentiable, and then it also had this condition about the endpoints being the same, right? Those were my 3 conditions for Rolle's theorem. The mean value theorem is very similar. The conditions are looser. It has to be continuous and differentiable, but I don't have to have the endpoints being the same. Okay? Continuous and differentiable, only 2 things to test. But as long as I have something that's continuous and differentiable, what I actually have from the mean value theorem is the fact that there is a slope, f prime of c, that is the same as the slope between the 2 endpoint values. And this desperately needs a picture once you guys have written down those details. I mentioned at the very beginning that Rolle's theorem and the mean value theorem are really the same thing, but that Rolle's theorem is just a special case of the mean value theorem. So think with me for a moment. The condition that I don't have here is that the derivative or that the endpoints are the same, right? But what if they were? What if, looking at this equation right here, right, or that expression, what if f of b and f of a were the same? What would happen to what I just circled?
0.
You get 0. Right, so if I inserted one more condition right here that said f of b is equal to f of a, then this f of b minus f of a would be 0, and I would get f prime of c is equal to 0, right? So for that very special case, that's exactly what Rolle's theorem said. It said the same thing, but in the very special case where f of A and f of B were the same. So f prime of C was 0. So let me draw you a picture of what we actually get when we lose that extra condition in terms of the graph. So we're going to take, I'm going to try to draw a really nice graph for you. We'll see how that goes. Okay, so here's my A, here's my B, here's f of A, and here's f of B. Okay, everybody good so far? It's continuous and differentiable, right? Like my image matches the description I should have. If I were to find the right-hand side, this piece right here, this is actually just an expression for slope. F of B minus f of A over B minus A. It's y2 minus y1 over x2 minus x1. Okay, that's all it is. So what this is actually finding on the right-hand side is the slope right here of this line. I'm going to do that in red, in a line. Okay, so the red part that I circled is the same thing as the red lines, the slope of the red line that I drew. Okay, everybody good with that? What this theorem is saying is that there is some C value somewhere in between A and B, mine looks like it's about right here, where the slope matches. Basically, I can't do it from my screen that you're looking at, but if you were to take my screen and you were to turn it on its side, it'd be that same picture that I had from Rolle's theorem, right? And all I've done is taken that Rolle's theorem picture, and I've turned it on its side to be slanted. That's all the mean value theorem is saying. Now, a direct application of this, fun fact for you, and this has actually been used and held up in courts of law, is that it's like a trap, right? So the police officers on the highway can sit at a certain interval apart, let's say a mile, for instance, or a mile apart. And they can actually calculate the time that it takes you from when you passed police officer number 1 to when you passed police officer number 2. And they can find your average speed. And they will know that at some point your speed was faster than that if they clocked you going slower over here and clocked you going slower over here. Are you with me? That's the mean value theorem in practice. Yeah. So the moral to the story is just be careful on the highway. All right, let's actually do one though. The determining whether the mean value theorem applies is easier than Rolle's theorem because I only have 2 conditions, continuous and differentiable. So we're going to determine whether the mean value theorem applies. And then if it does, we're going to actually find the C value that has these conditions. So you have one less condition at the beginning, but you have a little bit more work at the end. Okay, so the 2 conditions are continuous and differentiable. Is this function continuous and differentiable? Yes. Why? Yep, it's a polynomial. If you want to be real specific and say it's a square function, that's fine too, but it's a polynomial. Okay, so we know the mean value theorem applies. Mean value theorem abbreviation MVT. Okay, so what is the mean value theorem apply going to tell me then? Well, one thing I'm going to have to do that I didn't have to do before is I actually have to calculate the slope. F of B minus F of A over B minus A. Okay, so we're going to do that. So we're going to find F of, what are my intervals? 1 and F of negative 2. So grab your calculator, do it in your head, whatever it takes. What is F of 1 for the function x squared? 1. And F of negative 2? 4. Fantastic. All right, so I'm going to find F of negative 2 minus F of 1 over negative 2 minus 1. F of negative 2 was 4. F of 1 was 1 over negative 2 minus 1. So 4 minus 1 would be 3. Negative 2 minus 1 would be negative 3, right? What does this slope calculate to? 1. -1, sorry. I'm going negative in there. Yeah. 3 on top, -3 on bottom. So the slope is -1. Okay, so this is the new part of the problem. Didn't do that on the last problems because it was always 0. They were the same. The endpoints were the same. So what this is saying now is I'm going to be able to find a derivative. The derivative, of course, is 2x. And the derivative value will have a location where it's equal to the slope I just found. So the slope I just calculated is what I set it equal to, not 0 anymore. And of course, this happens, right? What is the x value where 2x is equal to -1? -1/2, thank you. You know, the sooner that you guys give me answers, the quicker the class goes, right? Just throwing that out there. Yeah, okay. All right, it's at -1/2. And is -1/2 between -2 and 1? Yep, it is. -2 is less than my -1/2, and that is less than the 1 value of my endpoints. We did it. We found it. One more problem, same directions. All right. This question needs, or has a function that's f of x equals 5 minus 4 over x. What kind of function is it? It's rational. And sometimes rational functions work, and sometimes they don't. It depends on the interval, right? So let's start with continuous. Is this function continuous on the interval -1 to 4? No, it's not. And if it's not continuous, it's also not differentiable. You guarantee fail differentiable if you've already failed continuous. Yes, sir?
How did you know that it's not continuous?
Good question. So there's several of you who are like, no, it's not. How did you know that it wasn't continuous? Yeah, because it's undefined at x equals 0. I can't plug it in. So the mean value theorem does not apply. Before you start packing up, I've got a follow-up question. Don't go leaving yet. So if you're working, this is why it's really important to check those conditions. Because let's just say, for instance, that you started through and you continued through the process here because you forgot to check for continuous and differentiable, and you all of a sudden turned the problem into something that took you 15 minutes to do. But if you checked these things first, you would realize you're done and the problem is over. And that would be so sad, wouldn't it? I mean, I would be sad for you. Okay? So make sure you're checking that it does or it does not apply. I'm going to change the interval, and we're going to work the problem where it does apply now, all right? Because I still want to work the problem out and show you how it would look if it were different. So I'm going to, you wouldn't change these rules if you were doing the problem. I'm changing them because I get to do that because I'm the teacher. Okay, yeah. Okay, but what if the interval were 1 to 4? Right? Rational functions are dependent upon their interval. Between 1 and 4, is this continuous and differentiable? Yep, it is. So it's continuous, it's differentiable. Hang on, check mark those. And the reason is because the only, I'll call it an issue, was at x equal to 0. And 0 is not between 1 and 4, so I'm good to go. Okay, so we continue down the process now because we have eliminated the one spot that was a problem, or at least the problem itself eliminated it if it had been set up as 0 as the interval from 1 to 4. So we find slope now. I need to find f of 1, and I need to find f of 4. And I didn't rewrite the equation on this slide, but let me do that real quick. So my function f of x is 5 minus 4 over x. Okay? All right, so what is f of 1? It is 1. And what is f of 4? So if I were now finding the slope, right, f of, we'll do 4 first, f of 4 minus f of 1 over 4 minus 1. So f of 4 would be, what did I just say? Was f of 4 4? And f of 1 is 1. That's friendly. I promise the slope's not always 1 and negative 1. Just happened to be the case on these particular examples. My slope ends up being 1 here. So what that's saying then is that I can take the derivative, and I'll be able to set it equal to 1 and solve it. So what is the derivative of f of x? Well, it might help to rewrite this like this. Right? All right, so what's the derivative of 5 minus 4x to the negative 1? What was it? Close? The negatives cancel, so it is positive. Yeah, you're right. Thank you. Yeah, so the 5 goes away. The negative 1 times the negative 4 gives me a positive 4. X to the negative 2. Everybody good with that? And then he put it back in the denominator. Excellent. 4 over x squared, and I should be able to set this equal to 1 and solve it. That's what it said, right? So if I were to set this equal to 1, how can I multiply by x squared instead, Emma? Okay. So like that? Are you okay with that? Awesome. So what are my x values?
Plus and minus.
Yeah. Good job remembering the positive and negative. Okay, it is positive and negative 2. But the negative doesn't matter. Why not, Maurice? What was that? It's not in the interval. So our C value is actually only the 2, because the 2 is the number that's between 1 and 4. Now, if my interval had been negative 1 to negative 5 or something, then we would be looking at the other value, right? I mean, it would be the negative value, but this one's 2. So the C value that I was told that I would be able to find, and then I did find, is actually C equal to 2. All right, so you have 2 homework assignments over break. Neither one have written work, though. They both are web assigned work. So, I mean, that's a long time. I would encourage you not to wait until the Monday you get back, because that's a really long time to not remember anything we just talked about. So try to get some of it done if you can, either before you leave or over the break, so that you're not trying to catch up over so much when you get back. And I will see you guys on Tuesday, like 12 days from now. We do have a quiz. Thank you so much for reminding me. We have a quiz over 3.1 and 3.2 as well on Tuesday when you come back, okay?